All right, so I want to start with just some announcement stuff, and then we'll take some homework questions and get the show on the road. I put an announcement on the class page in My Notre Dame. I don't know if anybody saw it or not yet, so I'm going to talk about it now. I've scheduled test 4 for Thursday of next week. I know that's a quick turnaround. In an effort of fairness, because of this, I will offer you the opportunity to make like a sheet of notes that you can bring with you into the test. One standard size sheet of paper, you write on front and back, has to be handwritten. You can put whatever you want on there, definitions, theorems, formulas, whatever. And it needs to be turned into me before the test. So let's say Tuesday. I think that's our next class. And I'll pass it back to you on Thursday for the test. Everybody okay with that, Jacob? Standard size sheet of paper, front and back, handwritten. Sound fair? Yeah. Okay. Could be worse, right? Like, oh, not already, another test already. Well, at least there's that. The idea here is that I think the week we get back from Thanksgiving break is the only week left to do testing, and I think Kairos is going on at that same time. So like, that's all of probably a lot of you guys getting hit by that. So we're gonna cram it in, and we'll just make some concessions to make things a little bit easier. Sound fair or fair-ish? Okay. Yeah. Okay. Sure. If you're happy, I'm pretty ecstatic about it. So, all right. Now moving on to questions from 4.1 and 4.2. If anybody has questions from 4.1 and 4.2. So we worked on those last time. Okay, fair enough. Everybody seems quite busy, and maybe we didn't get a chance to get too much of a start on that. That's fine. Today we're doing 4.3 and 4.4. That'll make Tuesday the review day to kind of get caught up. Everybody's okay? Okie dokes. Here we go. 4.3. Yes, lock it in. All right, so what we're going to be looking at in section 4.3 is going to be what can the derivative tell me about f, specifically about the shape of f. So we looked at in 4.1, we found a method for finding the absolute maxima and minima in a function, provided it was a continuous function on a closed interval, right? If you lose either one of those, all bets are off about how to find those things. But this will be very much the extension of what we started in 4.1. So the first things first, I can tell where my function is increasing and decreasing just by looking at where the derivative is positive and negative. All right, we've talked about this idea already, fairly straightforward. So if I look at an example here, I want to find where this function is increasing or decreasing, I'll simply take the derivative. Everybody's cool? I'll set that equal to 0. So I'll divide both sides by 12. I can then factor out a greatest common factor of x. The remaining quadratic is factorable, x minus 1 times x, or x minus 2 times x plus 1. So the places where my graph is equal to 0 is 0, 2, and negative 1. So I'm going to compute a sign diagram just like I would have done in my Algebra 2 class to solve like a polynomial inequality. So I'll pick a test value from kind of each of these gaps in between. Nothing fancy about the numbers I'm picking. I'm just like wanting to pick something that's going to be easy to deal with. And then I'm going to just compute f of like negative 2, or f prime, excuse me, of negative 2. So when I do that, I'm going to get negative 8 minus 4 plus 4, so that's negative. So it tells me that the interval from negative infinity to negative 1, f is decreasing. Is that okay? What's up?
Is it negative infinity to negative 1 or to negative 2?
To negative 1, because this is where it's equal to 0, right?
Oh, okay.
But I know it hasn't crossed the x-axis anywhere or had anywhere where it was undefined, right? So the only place it could get below is at negative 1, right? Is everybody okay there? So then we'll do the same thing for each of these. So if I do f prime of negative a half, I'd get negative an eighth minus minus a fourth plus 1. That's going to be positive. If I plug 1 in, I'll get 1 minus 2. That's negative. And then if I plug 3 in, I'll get 8 minus 4 minus 6. So that's negative again. Well, I'm plugging into this, but it's going to do the same thing as if it was the one with the 12, plugging into the derivative. Like if I take, because the other one is just a multiple of 12 more. So if it's positive, if I multiply by 12, it's still positive. If it's negative, I multiply by 12, still negative. That's 8. Oh, I'm sorry, that's not right. That's 27. Sorry, 27 minus 9 minus 6. That's positive. Excuse me. So I know then that f is decreasing from negative infinity to negative 1 or from 0 to 2. And f is increasing from negative 1 to 0 or from 2 to positive infinity. Does everybody feel okay doing this? Very much what you did to solve like a quadratic inequality way back in Algebra 2. This should look familiar drawing these sign diagrams. Yeah? Okay. Very good. This leads us directly to what's called the first derivative test. So the first derivative test I can use on a continuous function to find the local extrema, the local mins and maxes. So it simply says if my derivative changes from positive to negative, that's a local maximum. So if I go and I look here at 0, where we change from positive to negative, that's a local max. Everybody's okay there? The next one says if I change from negative to positive, then it's a local min. So that negative 1 is a local min, and negative to positive 2 is a local min. And if I have no sign change at all, if it goes positive, positive, or negative to negative, it's nothing at all. Does that feel okay? It's the first derivative test, so I can combine that with what I had done in 4.1. If I have a closed interval, I can find the local mins and maxes now on that interval, and then test to see which ones are, along with the endpoints, are the absolute mins and maxes. Does that feel okay? So these two sections, I think, are natural complements to each other, and this is just kind of justifying what's going on, right? Like, look at this as a max, where we change from positive to negative on the derivative. This is a min, where we change from negative to positive at the derivative. This is nothing, because I'm going from positive to positive. And this guy is nothing, because it's going from negative to negative, or decreasing to decreasing, right? Negative derivative to negative derivative. Does that feel okay? So just to kind of put a picture with what that theorem is saying. So I usually am always thinking about this in my head. I'm like, increasing to decreasing, that's max. Decreasing to increasing, that's min. So it's easy to kind of keep it straight if you just kind of like draw a picture in your head, which one is which. So we did this already. We just did it. Find the local min and max values for f from a function, or from example 1. Let's do this one here. Find the local min and max values for this function. G of x equals x plus 2 sine x. And we're on the interval from 0 to 2 pi. So I'll start by just doing the derivative. And I'll set that equal to 0. So cosine x is negative a half. All right, without your unit circle, what are the solutions to this? Which quadrants are we pulling from? 2 and 3, right? Because the x is negative, cosine is x, right? All right, so it's negative a half, so on my unit circle, it's the one that's closer to the vertical, correct? So this one here is it 2 pi over 3, or is it 5 pi over 6? Which one's bigger? 5/6 is bigger than 2/3, right? This should be 2/3 pi, and then what's the one down here going to be? 4/3 pi, right? Does everybody feel okay there? So what do you want to pick as our test value here? 0. Pi. 2 pi? Sounds good. I might have done 3 pi over 4, but that's whatever. All right, so when I plug this in then, f of 0, 1 plus 2 times cosine of 0. What's cosine of 0 without your unit circle? 1. So that's positive. 1 plus 2 times 1. And then if I do f prime of pi, that's 1 plus 2 cosine of pi. What's cosine of pi? Negative 1. So 1 plus 2 times negative 1, well, that's a negative. And then cosine of 2 pi is the same as cosine of 0, right? Because 0 and 2 pi are in the same spot on the unit circle. So 2 pi over 3, is it min or max? Going from increasing to decreasing, right? That's a max. And then 4 pi over 3 is going from increasing to decreasing. It's a min. Does that feel okay? Isn't this easy, relatively? Like the math part of it, like the symbol pushing, really pretty straightforward, right? You just have to like make sure you're using the function, the derivative, and the second derivative in the right ways. But for the most part, pretty easy, especially the algebra pieces of it. Like, very nice. Yes, sir. The next thing we'll define is the concavity of a curve. So that's like how it's bending, right? You guys are familiar with the term concavity. You've talked about concave up and concave down, probably especially with regard to quadratics, right? Concave up means it's like a cup. It'll catch water in it. Concave down is like an umbrella. The water will run off of it. So this is the technical math definition of it. It doesn't really matter for what we're doing. So this is concave up, right? If I dump water in here, it would catch it. This is concave down. If we dumped water on here, it would just kind of run off. Everybody's cool? Okay. So if I look down at this guy here, we're going to label each interval as either concave up or down. From A to B, concave down. B to C, how about C to D? D to E, up. E to P, up. And P to Q, down. Everybody cool? Okay, we can check for concavity using the second derivative. So if the second derivative is positive, we have concave up. If the second derivative is negative, we have concave down. Where the second derivative is equal to 0, we have a special name for that. Oh, no, we don't. That's still just like a critical point for the first derivative. But if you have a change in concavity, going from positive to negative, that's called an inflection point. So like B is an inflection point, C is an inflection point, D is an inflection point, E is not, and P is an inflection point, where we're changing concavity from either concave up to concave down or vice versa. Everybody's okay with that? Those will all be where the second derivative is 0. But this is not an if and only if statement. Just because the second derivative is 0 does not guarantee it is an inflection point. Everybody's okay with that? All right. So that's what we defined here. So if I want to sketch a graph based on information, let's kind of do that. So I'll draw like a little bit of a curve. Let's see, what are the x's I care about? -2 and +2. And then the y's I care about are -2 and 0. So when I look at this piece here, that's telling me what? Limit goes, or as x goes to -infinity of f of x equals -2. That's a horizontal asymptote, right? If I have a limit as x goes to infinity or -infinity, that's a horizontal asymptote. That's our definition. So I know this end, either like the graph is going to be doing this or it's going to be doing that, right? Probably the first one based on everything else in the picture, but we don't know for sure. And this one, also a horizontal asymptote. So again, either the graph is going to be kind of doing that or that. We're not sure yet, but it'll be doing one of those. Is everybody okay? Okay. From -infinity to 1, we are increasing. And then from 1 to positive infinity, that's a terrible color to pick, Mr. Kulik, we're decreasing. Everybody's okay? So what is that going to tell me right away? Is that it can't be that side, because if I have to increase, I'd have to cross my asymptote. I don't want to do that. So it tells me it has to be above that horizontal asymptote at -2. Everybody's good with that? Likewise, if I'm decreasing, I'd have to be coming down to this one. So it'd have to tell me that the graph has to be above the horizontal asymptote on the positive side. Everybody's okay with that? Okay. Then let's look at the next piece. So the second derivative is positive from -infinity to -2. That's concave up. And also from 2 to positive infinity. And then this one. And then in between here, we are concave down. Everybody's okay? All right. So I'm concave up and increasing until I get to here, which I switch now to being concave down, but I'm still increasing until I get to here, right? Now I'm going to switch from concave, or from increasing to decreasing, but I'm still going to stay concave up until I get to here. And I'm going to continue decreasing, but I'm switching to, or I'm sorry, I was concave down before. Now I'm switching to concave up. So it should look something like that. Is everybody okay with how I kind of sketched that information on there? My suggestion to you is to very much color code things kind of the way I have, to figure out like where things need to change at, to sort it out, because it can be overwhelming to look at all that information all at once. Is everybody okay with how I sorted that? Okay. That can be challenging. The last piece here, or the last idea in this section, is called the second derivative test. So the first derivative test and the second derivative test do the exact same thing. They're both a way to identify whether a critical value is a local minimum or a local maximum. They're doing the exact same thing. They're just using different tools to do it. So the first derivative test requires you to find a value on either side of your critical value and look for a sign change. The second derivative test is asking you to find the second derivative and then evaluate that critical value using the second derivative and check to see whether that number is positive or negative. So you only have to plug in one number in the second derivative test, but you have to take a second derivative. For the most situations, you will be able to do either one. You'll have enough information to do either one. In that case, it's a matter of preference, whatever you feel like doing. In some rare cases, specifically when you have like implicitly defined curves, the second derivative test might be the only one that's possible to do. So that's the only advantage of the second derivative test, is that when you have a derivative that's like x plus y, right? So like if x is 1 and y is -1, there's a derivative that's, the first derivative is 0, right? So that's a critical value. How am I going to do testing points when I have x and y on the same thing? Does it make sense to try to do a first derivative test there? You just do a second derivative test and just plug your 1 and -1 back in for x and y and check again. So that's where the second derivative test is most useful. I'll show you an example here in a second. All right. So if we look at the curve y equals x to the fourth minus 4x cubed with respect to concavity, inflection, and local mins and maxes, and when we use that to sketch the curve, boy, that's a lot of stuff to do. All right, we'll start with the first derivative. That's our first derivative, right? So we'll set that equal to 0 because we'll look for our critical values first. So those are critical values, right? Notice when I've been finding these critical values, I've been ignoring the possibility that the derivative doesn't exist. Why was I able to do that for all the situations up to this point? They were polynomials, right? So I know the derivative exists everywhere. There's no place where the derivative fails to exist. I should probably have said that, but I just went bulldozing past it. Is that okay? So far, so good? Now, since I also want concavity, rather than doing a first derivative test, I'll just do a second derivative test here for this, because it'll probably just be easier. So there's that. So 3 squared is 9. 9 times 12 is 108. And then 9 times 24 is 216, I think. Either way, that's negative. So this is neither local min or max, because the second derivative was 0 there. 3, I should say x equals 0, is negative, so that tells me that it is a local max. Is everybody okay there?
Yeah. When you plug in 3, instead of 216, should it be 72?
Oh my gosh, yeah, because I did 9. Thank you. So that's positive. So it's a min. Thank you. Yeah, I was plugging 9 instead of 3. Ugh! Mr. Kulak, come on. Get with the program here. Is everybody okay? We've got the local mins and local max done, right? Okay. Now let's do our concavity. So I'll take my second derivative and set that equal to 0. So I have x equals 0 and x equals 2. So far, so good. So let's do our concavity test here. So I'll pick x equals -1. I'll pick x equals 1, and I'll pick x equals 3. I guess where do I use y? So if I plug -1 in here, I get a positive, right? Positive times negative, or minus 24 times negative. And then if I do plug +1 in, I get 12 minus 24, that's negative. So x equals 0 is an inflection point because we changed concavity. If I do plug 3 in, that's the same thing that we did up there. That's positive. So going from negative to positive, again, that tells me 2 is an inflection point. Does everybody feel good so far? To sketch this thing, I would probably get some additional information. So I would probably also do increasing and decreasing, because it makes drawing my picture a little bit easier. So if I plug -1 in, I get negative minus negative, so that's negative. If I plug 1 in, I have 4 minus 12, that's negative. So this is neither, that's what we saw before. If I plug 4 in, that's 64 times 4, so it's 256 minus 12 times 16. Well, that's still going to be positive. So that was our local minimum. Now let's go and try to draw our picture then. So I care about 0 and 2, and then 3. So let's do some color coding here. So we'll do less than 0, and then greater than 2 is concave up. And we'll say 0 to 2 is concave down. And then we'll do orange for increasing. So that's greater than 3. And we'll do like purple or something for decreasing, which is less than 0 and then 0 to 3. Everybody's okay with this? Now look at the degree of this. What's the degree of this polynomial? 4, and the leading coefficient is positive. So I have like this type of shape, right? Now there could be some like loopies in the middle, but I know the end behaviors are going to be like, you know, going like that. Everybody's good? All right. So we're concave up and decreasing all the way until we get to like, till I get to like 0. And then it changes to concave down. Let me draw that a little better. And we're still decreasing, so it's going to do like one of those. Okay, come on. Until we get to 2, where it switches then to be back to concave up. So we're still decreasing until we get to there. And then we switch to increasing and we're still concave up. So it kind of looked like that. Is everybody okay with the picture I drew there? Now, do the y coordinates for any of the points that I made in there matter? No, man. Just we're looking at the general shape. All I'd be looking at is that you're increasing and decreasing and concave up and concave down in the right spots, and that your end behaviors hit. Everybody's okay with that? So again, I'm going to skip these last 2 examples because they're just doing the exact same things here. Just everybody's okay? Yeah, Michael?
You like go back like just like what was each part of the calculations for?
Okay. So this was, along with this, was my local maxes and mins. And then concavity was this, and then this. And then we had points of inflection was, looking at that stuff, right? Was still using this, and this, right? And then this was just like bonus for increasing, decreasing. You could have also used this to find the local mins and maxes though too. Is that what you're looking for? Okay. Did the color coding help? Perfect. It's probably easier than explaining it again, right? Because some of this stuff we use more than one place, which is the hope when you're doing this, not to have to repeat a bunch of calculations over and over and over again. All right. On to 4.4 then. 4.4 is circling back to limits. No, that's a good thing. And we're going to get the skeleton key for like all these limit problems that were a pain in the butt before, that we couldn't just direct substitute our way through. We now have the skeleton key to turn them into direct substitution problems. That's exciting, right? So if you remember before, we had talked about there were like some indeterminate forms where if you get one of these guys when you do your direct substitution, it doesn't tell you anything about the limit. It's okay, you have to do something to cancel something out or like rearrange it or something to get it to where I can do a direct substitution later on. We're going to skeleton key like you can do the same thing now every single time to get around an indeterminate form. That tool is called L'Hopital's rule. So L'Hopital's rule says that if I am doing the limit as x approaches a of f of x over g of x, and when I do a direct substitution, f of a over g of a gives me one of these indeterminate forms, then I can simply take the derivative of the top and the derivative of the bottom and try it again. And I can do that as many times as I need to get to a point where I can do a direct substitution. So the idea is you start with the direct substitution. If it works, you're done. If you get one of these indeterminate forms, we take the derivative of top and bottom, see what we get, and we do another direct substitution. If it works, you're done. If we get an indeterminate form, we do another derivative, and we just kind of keep hammering that, doing it that way. Is everybody okay with the plan? Isn't this wonderful? Like, no more like, oh, I got to multiply by the conjugate or like do some like, like it's, everything is now a nail. You have the biggest hammer in the world. All right. So the first step is we do a direct substitution. So I have natural log of 1 over 1 minus 1. What's the natural log of 1? 0. You all need to know that. When I ask that, you should be able to all spit that out. That's something I'd expect you to know on a non-calculator portion of a test, that the natural log of 1 is 0. So that's an indeterminate form, right? So I'm going to do L'Hopital's rule. So the derivative of the numerator is 1 over x. The derivative of the denominator is 1. Everybody's good? So now if I do a direct substitution, I get 1 over 1 over 1. Well, that's just 1. And I'm done. Rock and roll, Mr. Kulik. This is what I've been looking for. Why didn't we do this earlier? Because we didn't know how to do a derivative earlier. We needed the limits to define the derivative. So we had to do the limits first. And we couldn't use this because we didn't have the derivative yet. It's a vicious cycle. All right. Let's look at the next one. So again, we'll start with a direct substitution. So if I'm plugging in infinity, that's like e to the infinity over infinity squared or really just infinity over infinity, right? That's one of the indeterminate forms. So we just do L'Hopital's rule. What's the derivative of e to the x? E to the x. What's the derivative of x squared? 2x. So I do another direct substitution. Oh, rats, I still end up with infinity over infinity. What do? L'Hopital again. Derivative of the top, still e to the x. Derivative of the bottom is 2. When I do my direct substitution now, I get infinity over 2. What's that equal? Infinity. Woo! Buddy, Mr. Kulik, this I like. Are you kidding me? Like the limits were so hard before. This makes it so much easier. Just FYI, in the midterm, if I have limit questions, this is now a tool that you could use instead of doing like any of these algebraic workarounds. You can still do the algebraic workarounds if you'd like. Yeah, Michael?
So when you use it, you have to like write out H.
That's what I do, so it's clear to the reader like what I did. That's pretty standard. All right, let's go again. So if I do a direct substitution, when I plug infinity in, what am I going to get? Just infinity over infinity, right? Now, I can't have that. So L'Hopital. So derivative of 1 over x is? I'm sorry. Sorry, I said it. Yeah, you knew it. What's the derivative of the cube root of x? Now, if I plug in infinity for this, what do I get if I do a direct substitution as it's written currently? Right, 1 over infinity is 0, right? And then like infinity to the negative is like 1 over infinity again. That's still 0, right? So did I accomplish anything? But guess what I would do here? I might, see how gross this looks? I might try to clean this up a little bit and see if maybe doing that gets me a way out of this. So what if I write this as 1 over x over 1/3? Oh, let's say 1 over 3x to the 2/3. So that's like multiplying by a reciprocal to divide those. What am I going to get then? Does everybody see cool with how I got there? So I didn't do a L'Hopital here. I just did some like rearranging or some reducing. And if I do a direct substitution now, what am I going to get? 0. Yes. So don't just go hammer crazy with the L'Hopital rule. Sometimes you have to let's look at what we got here. This looks like something can reduce maybe. Let's just cool our jets and maybe see. Because if I did L'Hopital again, it's just going to you're just going to keep getting x's on top with negative exponents, x's on bottom with negative exponents, and you're never going to end. You just can keep going. It's like, Mr. Kulik, what happened? It's like, man, you need to stop a long time ago and just try simplifying stuff down a little bit. Is that okay? So far? Okay. Let's do another here. So if I do a direct substitution, tangent of 0 is, should be one you guys can do without a unit circle or a calculator. Nope. Tangent of 0, remember tangent is sine over cosine, right? What's sine of 0? 0. So what's tangent of 0 going to be? 0, because we know cosine isn't 0 at the same time sine is, right? So that's a L'Hopital. All right. So let's do it. Or indeterminate form. Derivative tangent is secant squared minus 1 over 3x squared. So if I direct substitute again, what's secant of 0? It's 1 over 0, which is, what does that mean? Well, that's infinity, right? For our purposes anyways. And the bottom is still going to be 0. That's one of those forms, right? Oh, maybe it's not. What am I doing here? What was the point of this example? Let me look here real quick. Secant. Okay. All right. Oh my God, no it's not. Cosine of 0 is 1, guys. Sorry. All right. So that's still indeterminate, so let's L'Hopital again. What's the derivative of secant squared minus 1? So it's a chain rule, right? The outer function for secant squared is x squared, so I'm going to have 2 secant. And then times the derivative of secant, which is secant times tangent. And then the bottom is 6x. So far, so good. So maybe I write this, simplify this down. So I have limit x goes to 0. I have secant squared x times tangent over x. Oops, 3x. Everybody's still good? So let's check. So secant of x squared is 1. Tangent of 0 is, or sorry, secant of 0 is 1. Secant of x is 0. 3 is 0. That's a bummer, but if we do this and like separate that out, this is really the indeterminate part, right? So you guys see that? So guess what that allows me to do? So I'm just going to have 1/3. Actually, I'm going to pull that whole 1/3 out front. So that 1/3 from there is that 1/3 there, which came from this piece. You guys see that trick? Why did I want to do that? How much easier is the derivative going to be of just tangent versus secant squared times tangent? The derivative of secant squared times tangent stinks, Mr. Kulik. Stinks. I don't want to have to do that. That's why I did it. So again, like as I'm doing the direct substitution, if I get like one of the pieces constanting out, I can just take that constant parts and pull it outside the limit and just leave the indeterminate piece and differentiate that. Do you guys see that? It's a nice trick. Can make these problems quite a bit easier. Now we'll L'Hopital one last time. The derivative of tangent is secant squared. The derivative of x is 1. So when I do a direct substitution, that's just going to be 1 over 1. So I'm left with 1/3 times 1, or just 1/3. Does that feel okay? So this is the limit as x approaches pi from the left. So sine of pi is 0, right? And cosine of pi is -1, right? Oh, well, that's easy. We're done. No L'Hopital necessary. The direct substitution just works, right? You have to check that initial direct substitution. Don't go blindly plowing in and using L'Hopital all willy-nilly. If you do it when you don't need to, you will get the wrong answer. Okay? Have to check first. Is that okay? All right. What if they're not written as a fraction from jump? L'Hopital requires the part inside my limit to look like a fraction. Well, I'm going to just do some rearrangement. As long as they're multiplied to each other. Oh, I guess let's do the direct substitution first, right? Hold on a second, Mr. Kulik. You just got done telling me that we need to check. So I get 0 times, yes. Sure. You got 0 times infinity. That's one of our indeterminate forms. But I can't L'Hopital this because that part's not a fraction. So here's the trick. I'm just going to pick one of the two pieces of my product, put it in the denominator, and put a -1 exponent on it. Which one would be make the more sense to do that to? The x or the ln x? The x, right? Like, I don't want to do ln x to the -1 because now that's a chain rule. X to the -1, still just a nice little power rule. Could you do ln x to the -1 and have it be fine? Yeah, but like, don't make your life harder than it needs to be. Our lives are hard enough. My teacher just dumped his calc test on me next week. And I probably have like 8 other tests going on next week also. So I'm like kind of salty about it. My life is hard enough. So there we go. We're in the form to L'Hopital this. So if I do a direct substitution now, plugging 0 in, 1 over 0 is like infinity over 1, so that's just infinity. Everybody happy there? Oh my God, no you're not. Get the heck out of town, Mr. Kulik. The derivative of x to the -1 isn't 1, you doofus. Right? That's going to be infinity over infinity. We don't like that. And you know what I'm starting to wonder? I wonder if maybe if we had done it the other way, the nastier way, maybe that is maybe that'll be easier. Because I really expected that to work from first crack. Oh my God, Mr. Kulak. No, 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 don't do this. This is bad. Don't do that. Don't do that either. What did I not notice here, guys? Yeah. What's that just going to give me? Just give me like negative x, right? Goodness, great googly moogly, Mr. Kulak. You're breaking your own rules that you showed us earlier. Sorry, guys. I just got excited and I got going too fast. Is that okay? Still doing fine? Yeah, Violet.
So ln0 is infinity?
Yes.
Okay.
Yeah. Because if you remember, what's the graph of the natural log look like?
Yeah.
It's actually negative infinity, but like either way. Is that okay? That's a tough pull from Algebra 2. It's like we graphed those things for like one day, Mr. Kulik. I can't remember what that looked like. AP expects you to. I'm sorry, I don't know what to tell you. All right. What if we end up with a situation where we have an infinity minus infinity? Again, if I start this one with a direct substitution, secant of pi over 2, well, cosine of pi over 2 is 0, so that's like 1 over 0. Tangent of pi over 2, well, tangent is sine over cosine. If cosine of pi over 2 is 0, that's something over 0, so that's infinity minus infinity. That's an indeterminate form, right? We don't like that. What we want to do is we want to find a way to write this as a fraction. We can't do that same trick because the two things aren't being multiplied together, but thankfully, if I just use a trig identity, I know that secant is 1 over cosine and tangent is sine over cosine. So we can just really treat this as 1 minus sine x over cosine x. And then if we L'Hopital this, that's going to be negative need my limit there. Negative cosine over negative sine. And now if I direct substitute, I get 0 over 1. So I'm good. That feel okay there? Violet?
Sorry, could you explain where you got infinity?
So this would have been 1 over 0 minus 1 over 0.
Oh.
And over 0 is infinity. Is that okay? All right. The worst ones are these indeterminate forms, where you have something like 0 to the 0, 1 to the infinity, or infinity to the 0. The other ones are relative pieces of cake. These ones are a little bit nastier, and I'll explain why you'll see why when I show you what we have to do here. All right, so if I do my direct substitution, I'm going to have 1 plus sine of 0 to the cotangent 0, right? Everybody's good with that? Sine of 0 is 0, so that's going to be 1. Cotangent is cosine over sine, right? So that's going to be 1 over 0, so that's 1 to the infinity. Is everybody okay with that? So that's one of our indeterminate forms. So somehow we have to get this to look like a fraction, to L'Hopital it. Not immediately obvious how to do that, right? So this is the trick. I'm going to think about the inside piece as like y equals this stuff. I'm then going to do like a natural log to both sides. So that's going to give me the natural log of y equals the exponent comes down to the front. So far, so good. And then I'm going to do that same trick I've done before. So I'm going to put one of these two to the denominator with a negative exponent. God help you if picked anything other than the cotangent. Like, I don't know what kind of a masochist you'd be to pick the other one, but yikes. Now, hopefully you recognize cotangent to the -1 is just tangent. Yeah. Those trig identities, again, Mr. Kulik, I still need to remember those. It makes life a lot easier if you do. Okay. So now what we're going to do is we're going to do the limit as x goes to 0 plus of the natural log of y, which is the limit as x goes to 0 of this thing. And I know since I haven't done any limits yet, and I evaluated the starting thing as one of these indeterminate forms, I know I can L'Hopital here. So if I do the limit of the derivative of the top, that's a chain rule inside of another chain rule. So I'm going to have 1 over 1 plus sine 4x. And then I have times the derivative of 1 plus sine 4x times the derivative of 4x all over secant squared x. Oops, forgot my limit. So if I try to direct substitute now, sine of 0 is 0. Cosine of 0 is 1. And secant is going to be, secant of 0 is 1 over cosine. Cosine of 0 was 1, so this is just going to be 1 on bottom. And what am I left with here? 4, right? 1 over 1 times 1 plus, or times 4 over 1. But here's the catch. I'm not done. Just calm down. We're almost there. Okay? We're almost there. So remember, this is the limit of the natural log of y. We want the limit for y, right? So let's think about what we have here. So the limit as x approaches 0 of, we want to do e to the ln y. That'll be the same thing as y, right? Because the e and the natural log cancel each other out. Remember our limit rule that allows us to push our limit inside the function? So I can do this and push my limit inside the e to the... You remember that rule? The limit of f of g of x was just going to be f of the limit of g of x. Right? That's all I did there. Now we know the limit as x approaches 0 of the natural log of y is just 4. So we're going to be done. That last putting it back together piece is tricky. Here's the good news. The AP won't give you anything that's not already a fraction. Or maybe a product. Like that last type you won't see on an AB Calc exam. I won't ask you to do it either on a test. I will ask you to do it in the homework. I think that's fair because many of you will go on and you'll take, have 2 or 3 or 4 calculus classes ahead of you in your future. There's certainly be an expectation in your Calc 2 class that you're able to deal with something like this. So I think it's good practice beyond the scope of what I would want to evaluate you on. But if you're somebody that's like, I have an engineering career in my future, might want to spend a little bit of time here and at least get yourself familiarized with something that you will end up having to do in your Calc 2 course. Does everybody feel okay? All right. That wraps up all of the topics I have for test 4. I'm going to skip doing the last example because we have 13 minutes left or something of class. I just don't want to do it. Because we've been ripping and roaring. Okay. So I know that the assignments are now feel like a lot of questions all at once, right? Because we've gotten all these things all in a couple of days, right? I probably need to make some kind of concession for this. I'd have to really look at them to do that. So my suggestion to you would be like, just do as much as you need for these 4 homeworks. Okay? Like do some, but like after a while, if it's like, I got the idea here, you can skip some and go to like a next kind of problem. It's like, okay, this seems different. I'll let you use your judgment. If you complete 50% or more of these, you're fine. Okay? I'll leave it to your discretion on which half you want to complete. Don't just start at the beginning and go, because stuff at the end might be a little bit different. Or if something is like, this is just like impossibly too hard, you can probably skip that for sure. But like, do enough to where you feel like you got a flavor of what's going on. Do the stuff that resembles the examples in the homework. Okay? Do the stuff that resembles the examples in the homework. Don't feel like you need to like, do every single one of these. You don't. Let's be honest, right? There's too much, too quick. But you do need to do some. I don't have like an hour right now to sift that through and look at every single one of these problems and like decide which ones are good ones and which ones aren't good ones right now. I'm just going to let you guys pick and do some. Like half-ish is fine. If it's not exactly half, whatever. If it's close. Okay? You guys feel okay? Reasonable compromise? Okay. Sure. Sure.